Today we're going to talk about internal flow. So we're starting kind of a newish chapter of the course. So this whole module that we're in right now is about Bernoulli's equation and extending it to internal flow. So today we're going to talk about what internal flow is and some kind of key properties. So there'll be some relevant stuff for your project in here. Let's see, I'll review last lecture. So key points from last lecture, we talked about static, dynamic, and hydrostatic and stagnation pressure in Bernoulli's equation. We also talked about assumptions needed to apply Bernoulli's equation. So this, again, is a list of assumptions that I'll ask you in the final. It's quite important. It's also on your homework, so just good stuff to know. You might have heard, I think the wind tunnel engineer yesterday was mentioning they use Bernoulli's equation in some parts of the wind tunnel. Like, for example, they use the pitot tubes to measure the wind speed. So there's certain parts of that flow even that Bernoulli's equation applies to and that it doesn't apply to. I will say that there are many times where this is applied beyond this list. So the point of, I guess, a lot of things in this course are to give you the strictest assumptions. And then in practice with certain, I guess, assumptions or better knowledge of the problem, you have freedom to break these sometimes. But you don't have that freedom in this course, just to be clear. um, yeah, so today we're going to talk about internal flow, like I said again. So we're going to talk about general properties of what internal flows are and some definitions, and then we're going to get into the two types of losses. And then we're going to add those losses into Bernoulli's equation at the end of it. So today we're going to talk about volumetric and mass flow rates, an average velocity in internal flow, and Reynolds number, all that within the context of internal flow. We're going to look at laminar and turbulent velocity profiles and laminar turbulent pipe flows. We're going to be able to predict whether a flow is laminar or turbulent in a pipe. We're also going to talk about entrance length and entrance regions for flow in a pipe. So before I get into the notes, I was going to ask you your weekend plans, but let's just do a little Mentimeter about, so internal flows. These internal flows are probably the most, I would say there's a lot more internal flow analysis that's done in industry versus external flows. So internal flows are super common. Maybe you guys have ideas of some industries that apply internal flows. HVAC, turbo machinery, yep, both internal flows. So for example, the people that designed the HVAC in this building, HVAC in this room would have used really similar concepts that we're going to get to by the end of this lecture. Power generation, engines, yeah, oil industry definitely has lots of internal flows. Plumbing, hydraulics, all these are internal flows. Nuclear is a good one. So a nuclear reactor is basically a big internal flow, and anytime there's pipes, water parks, that's good too. So like water supplies in a water park. So on that topic of water park, that's a good one. So for example, a pool isn't considered an internal flow because it has like a free surface. So an internal flow is a stricter in that it's bound on all sides by a wall. So that affects the analysis we do. Yeah, mining, slurry, transportation. I'm not sure marine propulsion. I guess maybe like fuels or something like that flowing in a boat. Pneumatics. Cool. Yeah, I think medical is a good one. So for example, all the biological fluid flows are internal flows. So people study internal flows of blood in our um, I guess circulatory system. Not sure what you guys are laughing at. Yeah, so medical is a very good one, but also like lots of medical devices use internal flows. So you can see we have a super broad list here. This is probably more broad of a list than I could get if I ask you to talk about external flows, right? You probably come up with like aerodynamics, vehicle performance, that sort of thing. So internal flows are very important, and that's why we're going to spend a couple weeks on them in your Fluids 1 class. Are there any questions about industries for internal flows? Okay. So you can keep your Menti open. We'll come back to it. Okay. Cool. So we're going to go over first the definition of volumetric flow. So for the majority of internal flows, we're going to be considering circular pipes. So let's say we're looking at like a front view of a circular pipe here. And this circular pipe is filled with fluid. Say the area of this pipe, it's just the area of a circle. Area is A. So again, that's a kind of a cross-sectional area. So it has units of meters squared. Let's say we take this cross-sectional area and we move it with some velocity. So this is going to be like a side view here. So that blue arrow is going to be velocity. So when we kind of convect a surface, an area like that, with a certain velocity, we're creating a cylinder, right? A volume. So this is going to be a cylindrical volume. So that's capital V with the ticks. That's going to be volume. So the volumetric flow rate is basically the rate that this volume is being created. So the volumetric flow rate is V dot, and that's equal to that velocity, V, times the area. So V dot has units of meters cubed per second. I'll just put this underneath. So meters cubed per second equals meters per second times meters squared. So that's a volumetric flow rate. So I've done meters cubed per second, but this is like gallons per minute, liters per minute. Very common parameter that we need to look at in internal flows. So for example, your project, you have a target volumetric flow rate that you want to achieve in your pipe of, I can't remember what it is, it's like 0.05 meters cubed per second. Okay, so we can get mass flow rate from volumetric flow rate using density. So let's say we know a certain volume of fluid is arriving at a point, and we know the rate at which that's arriving. If we know the density of that fluid, all we have to do is multiply this by density and we'll get the mass rate of fluid that's going in. So m dot is rho v dot, which is rho v a. And that rho is the volume. It would be called the mass density, aka density. Any questions so far? This is pretty straightforward, I think. I just want to get us on the same page about what volumetric flow rate is. Okay, let's talk about flow in circular pipes now. So we're going to look at kind of a cross section of a pipe. So let's say we cut a pipe in half. So our internal flow, like I said, the definition of internal flow is that it's surrounded on all sides by walls. So what happens, assuming real fluids are viscous, right? What happens at the wall? We covered this before in the class. It sticks to the wall, right? So what, for a practical flow, what would we expect to happen there? Say the flow is going through this pipe like this. Flow is going to stick at the wall, right? So the center will be fastest, that's right. But what happens in the near wall region? What forms? Boundary layer, right? Yes, exactly. So our flow sticks to the wall and we get a boundary layer forming there. Like Aaron said, the flow is fastest away from the wall. So this is velocity profile in a circular pipe. Looks something like this. The actual shape of this we'll talk about later, but the important thing is that we get a no-slip condition at both of the walls. So this velocity profile is what internal flows are all about. Okay. Let's do a little bit of math here. So I'm gonna look again at the front cross section of this pipe. So again, it's a wall, right? So this is a wall. We know the no slip condition is going to happen there. So we have some sort of, what I'm doing right now is I'm setting up an integration. So let's set up a integration by considering a small element along this area. Okay. Wait a sec here. So this is kind of an area element. Okay, so the area of that circle there, so this is going to be a very thin element. I've exaggerated it here, so we don't need to consider this as area of a circle. The area of this is just going to call dA, and that's basically the circumference of this times some differential r dr. So the dA there is 2 pi r dr. Okay, so we can now integrate, say, our velocity distribution to get our mass flow rate over this cross section. I'm going to just define r as well. So r is 0 at the start. So this is r here. So r is a coordinate, and r is 0 less than or equal to r less than or equal to big R. And big R is the radius of this pipe. So our mass flow rate is going to be this integral. It's the area integral of rho u of r dA. So u of r dA is v dot, volumetric flow rate, so that's what we just saw up the top. Don't worry too much that this is a very small element. All we're doing is we're taking the area of that element and convecting it with a certain velocity. Now that velocity is determined by r. So if I go back up to that cross section here, see I annotated r in there. So the actual velocity we have, u of r, is determined by our radial position in a pipe. Okay, so the total mass flow rate then will be integral of 0 to big R rho u of r 2 pi r dr. Okay. Any questions on this integration setup? Okay. Maybe we can do a show of hands of who's looking forward to evaluating this integral. I didn't think so. The good news is we really don't have to evaluate this integral that much in this course. The reason I'm going through this is to give you the definition of an averaged velocity. So how can we define an average velocity so we don't have to worry about integrals? Because, for example, the people that designed the ducts in this room probably didn't do any integration across the cross-section of this ducts, thankfully. Okay, so we're going to define a an average velocity V average and that is defined such that, remember up above I said m dot is rho VA, where V is the velocity and A is the cross section. We're going to define our average velocity such that rho V average A is equal to this integral. Okay, so this area A, just as a reminder, is the area of a circle. So that will be pi big R squared. So our differential element, the dA of that, was kind of this area of this very thin element, but big A here is the whole cross-sectional area of our pi R squared. So this allows us to calculate, so with some rearranging that I won't do, the average is 2 over R squared, integral 0 to R, u of R dr. So this is the definition of average velocity. In most cases, this isn't something we need to regularly do, because for the rest of basically internal flows, we're just going to talk about average velocities along pipes. Today, we're going to learn a lot about the details of these profiles and how we get average velocities and maybe what's different between a laminar and a turbulent pipe flow. But for the most part, this average velocity is what we're going to use in internal flows. Let's talk about the velocity profiles that we get now. So this velocity profile u of r is clearly of a lot of interest. So I will give these non-dimensional profiles u of r over u max. And u max is at the center line. So CL means center line. And that's equal to, it depends on whether it's laminar or turbulent. So for a laminar pipe flow, that's 1 minus r squared over big R squared. For a turbulent pipe flow, it's 1 minus r over r, some exponent 1 over n. And typically, n equals 7. So that n there varies with Reynolds number, but we will use generally n equals 7 for the turbulent velocity profile. So these are velocity profiles in a smooth, circular pipe. There's one more qualifier, is that this is fully developed. So you might notice there's no dependence on where we are along the pipe in this velocity profile. That's what the fully developed thing means, and I'll talk about that later in the lecture. But these are basically some velocity profiles in a pipe. So I'm going to show you kind of what these look like, and then maybe I'll take some questions about these velocity profiles. Okay, so assume we have some really long pipe here. Again, this is just a circular pipe. Let's take a look at what these velocity profiles look like. So again, this is a pipe, right? It has a circular sort of frontal area that the flow is going along. So let's look at the velocity profiles in this pipe. So this, what I've shown here, is our laminar profile, the non-dimensional profile u over u max. So u max occurs here at the center line. Okay, and we have our no slip condition at the wall, so the velocity is 0 there. The relevant thing for pipes is the internal diameter, right? Because that's the diameter that the fluid is actually seen as it flows through this pipe. So this is going to be a confusing part of your project for a lot of you, but often pipes, when people say a diameter of a pipe, that might not actually refer to the internal diameter. But it's really easy to go. You can go look up on Wikipedia. There's a really like nice table of what the ID is for a given sort of standard pipe sizing. This is an important part of fluids analysis for internal flows. So it's always the internal diameter. So we generally don't care about the wall thickness of the pipe in fluids. The structural people will care about that. Because, for example, the wall thickness should be thicker if the pressure is higher in the pipe. So this is our laminar profile. It's, as we saw there, it's parabolic. It's a really nice parabola. This is our turbulent profile. So again, that's a non-dimensional profile there. You can see the turbulent profile is extremely steep near the wall. It doesn't look like it, but this actually goes to 0 at the wall there. So the laminar profile is much smoother. The turbulent profile is just you curve that down, so it's extremely high wall shear stress at the wall. The vast majority of engineering flows and pipes look like this. So away from the wall, it's a little bit more uniform. So let's compare now our turbulent and laminar profiles. Let me just. Okay, so the orange is our laminar profile, and the blue is our turbulent profile. So this profile here is the U over U max. So they get the same U over U max as here. But in general, these occur for different, very different sort of velocities in the pipe. So I'm plotting here the non-dimensional profiles so we can compare them to each other. Yep, questions?
Why doesn't Umax plateau? Why is it a parabola? Why does it reach the maximum at one point?
So where would you want it to plateau, I guess?
Over a region.
So you mean like if the boundary layer, for example, would be this thick, and then you would have a uniform profile?
Yeah, so why is it always assumed that the boundary layer is overlaps?
That's a very good observation. So the question is, why don't you get like a very small boundary layer and then sort of just a big uniform flow in the middle? In internal flows, yeah, for pipes. So the boundary layer, for example, for the laminar case, we're going to see later today, the fully developed boundary layer forms when the boundary layer on the top and the bottom of this connect. So you get this fully developed parabola. The turbulent case, there's less connection between the boundary layers, but it still happens. So that's why the turbulent case, for example, this is 1 over, with that 1/7 exponent, it's still quite uniform in the middle section. And for higher turbulent cases, it gets even more uniform in the middle, but you get a lot of wall shear stress. So does that answer your question? Yeah. Okay.
Uppercase R is the internal.
Yeah. Yeah. So uppercase R is this, and lowercase r is like this, where we are along there. Yeah, it's like a coordinate. Yep. Steve?
So if you had a sufficiently large pipe, you would have a plateau of velocity in some region in the center?
Yes. You could think like in the, say, extreme limit of an internal flow, say a pipe the size of this room or the size of this building. It would be unrealistic to expect those boundary layers to connect. But I'm talking here, we're going to talk about practical internal flows in pipes and engineering. So in that case, you get these profiles. Yep.
If I know most cases we assume like a smooth pipe.
Yeah.
But if let's say it was an older pipe and there's some like corrosion that's happened, would you get some like recirculation and like how would that affect the?
We'll see that later in this. It will affect the frictional losses. So we'll have higher frictional losses in pipes that aren't smooth, or they have some wear, or like different materials. Like it depends on the surface roughness. So that will all affect the turbulent profile. I'll mention the laminar profile is derived analytically. The turbulent profile, again, everything in turbulence is a little bit more complicated. That depends quite a bit, but in general, they look like this. They have extremely steep velocity gradients near the wall, and then they go to a more uniform in the middle than the laminar profile. Any other questions? Yep.
So the end is usually 7. So
Yeah.
this is the same 1/7. It's like all the other turbulent 1/7.
Yes. So the 1/7 is like a famous thing in the boundary layer. So that's it. You'll see that in fluids too. I don't really want to talk about that in this case. Yep.
So if turbulence like kind of comes from like experimental like approximate,
Yep.
how do you measure that like gradient? Like how do you? I feel like that's a flow on it.
That gradient is extremely hard to measure. That's right. The good thing is that say you were able to measure the drag on the wall, you could get that near wall gradient because that's what the drag on the wall. That's what creates the drag on the wall is the instantaneous wall gradient, right?
Okay.
I'll mention the turbulent thing. This comes from some theory and stuff too. It's just a lot more assumptions and stuff go into that. than the laminar case. So these are the non-dimensional profiles, U over U max. But in general, to actually achieve this sort of profile in a pipe, you would need very different velocities. So you need something like this. So these are dimensionalized profiles. So for example, the turbulent case occurs at a much higher Reynolds number. So if you fix everything else, it just occurs at a much higher velocity. So this is what your turbulent profile will look like. And a laminar profile, if you had a pipe and you could sort of change the velocity to get a laminar turbulent profile. So when you compare them directly on top of each other, it allows you to compare them easier. But in general, you'll see that what kind of happens as the turbulent profile is developed. So any questions about that? No? Okay. So these are our velocity profiles in a pipe. And the nice thing is that we usually don't have to care about the velocity profiles in a pipe that much. Yep.
Sorry, just one last question. With the with a flow meter, then is it measuring the average velocity or is it measuring? Okay.
Yeah, it's everything in internal flows in practice will be calibrated for the average velocity. Yep.
Thank you.
So turbulent flow just looked faster than laminar flow. Is it more efficient too?
Efficient is kind of a the drag is different in turbulent and laminar flows. I will say though, the overwhelming majority of engineering applications have turbulent internal flow. It's just kind of a fact of life because the flow rate required is high enough that you just have to have internal turbulent flow. Any other questions? So laminar internal flow occurs in very special cases. For example, these microfluidic chips, that's all laminar, like extremely small scale flows, laminar. But when it comes to internal flows, it's in practice going to basically be all be turbulent. So there's a hint for your project. If you predict that it's going to be a laminar flow to get that much water all the way from Lake Ontario here, it's going to be turbulent flow for your project. So our mass flow rate then in our pipe is going to be, remember this? M dot is rho V dot, which is rho V average A. I'll give some different expressions we could use. Rho V average pi r squared. Again, big R is the actual pipe diameter, but most of the time in manufacturing, they don't tell us the radius. They tell us the, sorry, did I say big R was the diameter? Big R is the radius of this pipe, but most of the time we are told about diameter because it's actually a little bit hard to measure radius directly, right? You're just measuring some point out in space that you're like, oh, that's the middle of the pipe. They don't like to do that. So they'll give us diameter, so that's V average pi over 4 d squared. So that is our mass flow rate in a pipe. Again, the volumetric flow rate is, maybe I'll give this, so V dot equals M dot over rho. So for your project now, you have a target volumetric flow rate. So everyone's design should achieve the same volumetric flow rate. You get to choose the pipe diameter in your project. So now you can look at what the sort of velocities will be for different pipe diameters in your project based on your choice. Let's talk about Reynolds number for pipe flows. So the Reynolds number is defined the same way. It looks the same. So Reynolds number sub d for based on diameter is rho v average b over mu. We can also write that as v average b over nu. Now, this Reynolds number looks the same as the previous one we did, but in your head, don't make any connections between the external flow Reynolds number and the internal flow Reynolds number. You know how I said it really depends on how we actually define these different parameters and these non-dimensional parameters? like it depends how we define the different variables. There'll be a completely different set of transitional Reynolds number criteria, things like that, for internal and external flows. So it's the same, it's called the same thing, but it's completely different. So don't think about external flow Reynolds number at all when you're doing this. So we're going to talk about, this is the following criteria. So if Reynolds number is less than about 2300, we get laminar flow. When it's 2300, so that less than with the squiggly means that it's about. This is all about. It's between 2300 and 4000. It's called transitional flow. So in transitional flow, sometimes it stabilizes and it's laminar, but then a little disturbance occurs and it starts going to turbulent and then it settles down and that sort of thing. If the Reynolds number is above 4000, you get fully turbulent pipe flow, which is the vast majority of time. So for example, the Reynolds number for transition before that we looked at was like in the millions, right? So this is a completely different Reynolds number. There's a different set of criteria for internal flow, transition, and external flow. I'm going to do a video now of kind of what this looks like. So there's actually an interesting piece of fluid mechanics kind of history here. So the Reynolds number is named after Reynolds, and this was actually the first Reynolds number. He was doing internal flows in a pipe. So this was the very first Reynolds number criteria. Then it was extended to the idea of external flows and things like that, using a really similar formulation. But this was actually the first kind of experiment. So this was the very first kind of Reynolds number that was created. Okay, so let's look at this. I'll explain this experiment a little bit. This is a little bit like what they were doing in the water tank yesterday, where he had that thing that was injecting dye in the water tank and it was kind of flowing. So what they have is a very similar idea. So a dye reservoir being injected into a pipe. So if the flow is really laminar and smooth, we just expect the dye to come out like that. But if transition starts to happen, the dye will start to get smeared around this pipe. So if we use a clear pipe, then we can look at that. So you'll notice they used a different number than I just told you. In this course, we're going to use 2300, but this is laminar flow. So you can barely see it moving. So that dye is not basically going anywhere for the laminar case. Now when we get into that transitional region, it's not steady anymore. So there's that motion there. That's transitional. This would be considered turbulent in our case, so 4,000 to 10,000. But again, the vast majority of engineering flows are actually much higher than that still. So the dye for turbulent flow looks like that. So those, you can kind of see it right at the end when it really picks up, like the dye is going everywhere. So the profiles I've given, you might notice they don't look anything like these squiggly profiles would be. The profiles for the turbulent case that I've given are kind of the average, because that's what we care about in engineering, the average. So that's what the original Reynolds experiment looked like. I'll post this on Learn because it's interesting, but this is the original, this is the paper from 1883 by Reynolds. So in this paper, he presents these different criteria. He didn't actually call it laminar turbulent, and he also didn't call it the Reynolds number because it was named after him because of this paper. It was termed at that time direct or sinuous. So he sort of thought these fluctuations are kind of like sinusoids, so sinuous. Now we call it laminar and turbulent. So that's quite an interesting one. So what we're going to do now is a little example. Are there any questions about the transition turbulent Reynolds number laminar?
When it showed the dye like kind of oscillating in that sense, could that like you know, for instance, like so it would create like a certain frequency with the air, like the Gilbert Bridge was creating that like resonance.
Yeah.
Is that similar happen inside a pipe or no?
Yeah, that can happen. That's a reason of some noise like in, for example, like a valve and an internal flow could be like noisy. You could hear the flow in the valve, and that's because you have certain resonances like that. That's more of a mechanical thing. Okay, so now we're going to do an example. So I'm going to give you a typical flow that I'm sure many of you have seen, and then it's your job to predict whether or not it will be laminar or turbulent. So let's consider flow through a gas pump. So say you're pumping gas in your car. Take a flow rate of say 20 liters per minute. The tubing, we'll assume it has an internal diameter of 3/4 inches. And I'll give you the kinematic viscosity of gas, which is about something like this, 5 times 10 to the minus 7 meters squared per second. And your goal is to estimate whether this is laminar or turbulent. Okay. So don't worry if you didn't copy that, because I have that on our Menti slide as well. Sorry, I think when I pressed X, it ended this, but maybe it'll reconnect you guys. Okay, so there's the question there on the right-hand side. So there's a little bit of unit conversion you'll have to do there, but when you're ready, just give an answer whether or not you predict this to be laminar or turbulent. Maybe if someone calculated a Reynolds number that they're getting, I want to share it. So yeah, this is going to be basically turbulence. Maybe I haven't given you enough time for all the unit conversions and stuff in this problem. I think I got a Reynolds number of about 44,000 for this. And the flow in the gas pump is not really a high-speed flow. It's not like a transmission flow for transmitting water between cities or natural gas or something like that. It's considered relatively low speed, and even that is well within the turbulent region. So this is where we see most real-world flows are going to be turbulent. So I'll go through this example just really quickly so we can see the numbers. Okay. So I got an average velocity of v dot over a. So that's 20 liters per minute times 1 meter cubed per 1,000 liters times 1 minute over 60 seconds. Area. So I gave you the ID in this case. So for certain pipes, you'll see below a certain size, when they say it's like 3/4 inch tubing or 3/4 inch pipe, that is the internal diameter. But at certain sizes, it's not the internal diameter, which makes it confusing. 0.75 inches, and then we'll convert that to meters. So that's 1.17. And the Reynolds number is V average times D over nu, which is above that. So 44,000 is well above 4,000. So that's sufficiently turbulent to say that. Okay, I think I have another Menti question on this example. So just answer yes or no of whether you think Bernoulli's equation applies to the flow through this gas pump. So So Bernoulli's equation I've written in there on the right hand side. Are you guys doing this on purpose? That's actually quite impressive. Okay, so does someone who answered no want to explain why they answered no? Yep, there. Right. Yes. Yes. That's a very good reason. Does someone who answered yes want to explain why they answered yes? Maybe not after Aaron's really good answer there. So Bernoulli's equation in this form doesn't apply to flow in most pipes. So we're going to extend this later on, but the reason is, like Aaron said, so it's pipes are, there's lots of viscous effects. So even in the fully turbulent case, all that mixing that we saw, the fact that there's boundary layers that are basically connecting, the flow in the pipe is dominated by viscous effects created by the pipe wall. That's kind of what really characterizes internal flows. So that frictional loss is why we have to pump. For example, you can't, there's no frictional losses in Bernoulli's equation, right? So if you applied Bernoulli's equation to a pipe, you wouldn't have to do anything to get water to flow at whatever rate you wanted through a pipe. It would just flow if you apply a little bit of pressure. So that frictional loss is what kind of characterizes Bernoulli's equation. It characterizes pipe flows and why we need to extend it to Bernoulli's equation. I have another one here. So does this continuity equation here apply to flow in the pipe? So yes, it does. Very good. So clearly I explained that part of the course better than Bernoulli's equation because it's a lot less split. So most liquid flows in pipes are considered incompressible, and we know that mass is conserved. So yes, the continuity equation applies to the flow in the pipe. How about the Navier-Stokes equation there? So not to single whoever answered no out, but is there like a reason that you're very confident about why it doesn't apply to flow in the pipe? Because it might help some other people too. No, that's fine. So yeah, the Navier-Stokes equation applies to every fluid. It's the most fundamental equation. So what I've written here is the Navier-Stokes equation for an unsteady, incompressible fluid with frictional effects, pressure gradients, and gravity effects in there. So that is basically the governing equation for flow in that gas form. So I would say yes, it definitely applies for flow in the gas form. I'm going to check what my next question is. Maybe we'll do this one before I tell you what this actually means. So do you think that the flow in the gas line will be fully developed by the time it reaches your pump nozzle? Meaning that, do you think the velocity profile will be changing by the time it arrives there? A lot of yeses. I can tell your splits, but I'll explain what fully developed means and some criteria for it very shortly. So maybe is there a reason why anyone picked yes or no other than just guessing that we could talk about? Yep.
I would imagine that when you're putting gas in your car, it doesn't have a particularly long and straight path to follow.
Right.
So there would be inconsistencies. Like, I imagine that it takes a while of going in a straight path for it to become fully developed with no changes. So that's
Okay. So you made a really good observation. So you think that over time it will eventually develop, right?
yeah.
Right. So do you have an idea why you think it will develop? Maybe related to boundary layers, right? Because I told you the boundary layers meet and then that's when it's fully developed. We also know that boundary layers grow as you move along the pipe. So once those boundary layers connect, we can consider it fully developed. So I'll talk about now what that looks like in terms of profiles. But I will say, I also talked about boundary layers, the turbulent boundary layers, they develop quite quickly. So I think it will be fully developed by the time it reaches the pipe, but your logic was really good and basically the entire concept behind developing flow. Yep.
How does going around a corner change the boundary layer?
We'll talk about that. That's complicated. and you don't have to know it for this course. The question was, how does going around a corner, say a curved pipe, affect the boundary layer? We will cover how it affects the pressure losses. For example, when pipe goes, say you're pumping through a flat pipe, and you pump through pipe that bends up and then bends right. Those bends create a pressure loss, and we'll learn how to account for that. But we're not going to do that in this lecture. So we're going to talk about entrance length here. So say we have some big tank or something like that that our pipe is connected to. We have flow coming like this. So our boundary layers will grow like this green line. At some point they'll connect. So the flow, we can assume it's, say it's uniform here. So it's going to do something like this. Until it's fully developed, it will look quite uniform in the middle. Go back to the wall. But once it's fully developed, we get those fully developed profiles that I showed earlier here. So once we get that fully developed velocity profile, the length until we get that is called LT. Or sorry, LH. That's the entrance length. We have some expressions here for rules of thumb. So LH over D, where D is the diameter again, for laminar flow is about 0.05 times the Reynolds number based on diameter. For turbulent flow, there are many expressions and it's much more complicated, but a common rule of thumb is just 10D. So 10 diameters away from the tank or whatever, you can assume the flow is fully developed. So if that, for example, the hose in the gas was 3/4 inch, so around like 7.5 inches from wherever the gas originates from, 7.5 inches along that hose, you can expect fully developed flow. So that's why it will probably be fully developed by the time it reaches your tank. But you're right in that the hose bends will create additional effects. This is for a smooth, flat pipe. So that second case is for turbulent. I'm going to make one more statement. I know I'm just a little over time, but this is a hint for your project. For the project, assume flow is fully developed everywhere. The reason that you can do that, and this is a common engineering assumption, is that the entrance region losses are accounted for in the minor loss analysis. Which we're going to talk about next week. Are there any questions about this? So just to emphasize, it's pretty much always assumed that you have fully developed flow, because even in this building, like 10D, 10 diameters of the pipe in this room is like there, right? So you can just assume the entire thing is fully developed, which is good because you don't have to try and account for these boundary layers plus that core flow region. You can just use all the other analysis we're going to do in this course, this part of the course. Okay, so have a good weekend, everyone. I'll see you on Monday.